From here, we're going to look at a more comprehensive bond theory called molecular orbital theory, often called MO theory for short. Notice that we use the abbreviation MO for the words molecular orbital. We're not going to spend a great deal of time contrasting the differences between valence bond theory and MO theory. However, I would point out one significant difference, and that is that where valence bond theory really limits itself to looking at how atomic orbitals combine to form bonds, MO theory goes quite a bit farther. With MO theory, we combine atomic orbitals to form molecular orbitals, where the orbitals are not constrained to be localized between two atoms. In fact, molecular orbitals may cover a much wider volume, including the entire molecule. Later in the course, when we look at benzene and similar molecules, that is, molecules which we call aromatic, we will look at molecular orbitals which illustrate this quite clearly. There are some key points I would like to point out about MO theory. First of all, we say that orbitals are conserved, meaning that the number of molecular orbitals formed for a particular molecule must equal the number of atomic orbitals which were used to construct those molecular orbitals. On the figure shown, you will see that we start with two atomic orbitals. These are the 1s orbitals of each of two distinct hydrogen atoms. We combine these to form two molecular orbitals. One of these molecular orbitals is said to be bonding and more stable than the atomic orbitals from which it was derived. Just a side note here, I just used the phrase more stable. This is equivalent to saying lower in energy. Now the other MO which is formed is called an antibonding orbital. It is higher in energy, that is less stable than the atomic orbitals from which it was constructed. Let's continue to look at the hydrogen molecule, since it is about the simplest example of molecular orbitals which we can consider. You will notice that whenever we have constructive overlap between atomic orbitals, we ultimately produce a molecular orbital which is more stable than the orbitals from which it was developed. For example, you will always see this when two nodes of the same color, that is the same phase, overlap on top of one another. So this gives us a bonding MO. On the other hand, whenever orbitals combine to give destructive interference, we end up with an MO which is higher in energy than its atomic orbitals. We've already seen that destructive interference generates a node. We see that in our antibonding MO for this molecule. Whereas in the bonding MO, the electrons spend most of their time in the region between the two nuclei, the opposite is the case for the antibonding MO, with electrons occupying it essentially forbidden to occupy the space between the nuclei, owing to the presence of the nodal plane in between the hydrogen nuclei that we see right here. For the hydrogen molecule, we have a total of 2 electrons to consider, one from each atom. Just like with atomic orbitals, we follow the Aufbau principle with molecular orbitals. So our 2 electrons must be placed in the bonding MO when the molecule is in the ground state. No electrons are available to occupy the antibonding MO. Overall, the hydrogen molecule is predicted to be more stable than the 2 atoms from which it was derived as a result of this favorable interaction. Now suppose at this point we want to consider a theoretical diatomic helium molecule. Now, at this point, that should seem absurd on its face. Helium is a noble gas, and from what you've learned so far, noble gases generally do not react, and certainly do not react with each other. Helium is particularly inert. Molecular orbitals for this molecule should be essentially the same as for hydrogen. In both cases, you are combining 2 atomic orbitals to form 2 molecular orbitals. However, since each helium atom has 2 electrons, as we see here and here, we now essentially have 4 electrons that can be used to occupy the molecular orbitals of the resulting molecule. Just as before, the first 2 electrons go into the bonding orbital. However, the next 2 electrons would have to fill in an antibonding MO. While the first interaction is stabilizing, the second one, that is the antibond, is destabilizing. In effect, a bond and an antibond between the same two atoms cancel out, leaving us with no bond at all. Now, at this point, you might want to review bond order calculations from general chemistry. The bond order for the hydrogen molecule is 1, corresponding to a single bond between the two hydrogen atoms. The bond order for diatomic helium here is 0, which indicates the absence of a bond. Ultimately, we would expect the He2 molecule to be less stable than the lone atoms by themselves. Helium remains in its atomic form rather than a molecular form owing to the destructive interactions from electrons occupying an antibonding orbital in the He2 molecule. If the molecule has an equal number of bonding orbitals and antibonding orbitals filled with electrons, then the resulting molecule will be generally less stable than the non-bonded atoms by themselves. Now let's consider a more complicated molecule. Here we see two molecular orbitals for the molecule bromomethane, CH3Br. Now we have 5 atoms coming together from the overlap of several atomic orbitals. These molecular orbitals that we see here were derived from some rather complicated calculations, which we will not consider here. And nowadays we rely on software to produce pictures of MOs like these. As noted on the slide, each one of these pictures represents a single set of molecular orbitals. The different colors represent different phases, just as we saw before. On the MO to the left, there are 2 lobes with a node in between. On the molecular orbital to the right, there are 3 nodes. You can see this in the color changes between the lobes. On the picture to the left, red and blue lobes here are separated only once by a single plane through this carbon and bromine atom. On the picture to the right, there are 3 points at which the phase changes, if we look at the picture and going from left to right. So between the red phase and the blue phase here, we have a node, and then between these regions here, we have a node, and between these lobes here, we also have a node. Just like atomic orbitals, molecular orbitals can hold at most 2 electrons. In the ground state, we expect the electrons to occupy the lowest energy molecular orbitals, following the Aufbau principle. For most molecules, this will mean that the higher energy molecular orbitals, generally the antibonding orbitals, will be unoccupied in the ground state. While it is true that molecular orbital theory does give us much valuable information about the bonds in a molecule, including information on bond strength, it is by no means a comprehensive theory. Let's take a look at one obvious deficiency of MO theory. Suppose we wanted to use MO theory to describe a methane molecule. We have 4 hydrogen atoms, which we will use their 1s orbitals in making bonds. The carbon atom has only 2 unpaired electrons, which we can use to combine with the 4 1s orbitals from the hydrogen atoms. Furthermore, carbon's electrons are in p orbitals, and we've already seen that these orbitals are at 90-degree angles to one another. Now, experimental evidence clearly shows that the shape of a methane molecule is tetrahedral, and we have bond angles of 109.5 degrees from the hydrogen-carbon-hydrogen bonds throughout. So we see that we cannot simply combine atomic orbitals in this case to produce a molecule which accurately reflects the methane molecule. Now, to address these concerns, suppose that we're going to make a little trick here, and what we will do is we will excite one of the electrons from a 2s subshell here and excite it into the 2p subshell. Now, this addresses one of the problems that we saw, in that we now have 4 singularly bonded electrons available for our hydrogen atoms to bond with here. However, this still doesn't resolve the problem of the bond angles. If a methane molecule were constructed using the set of orbitals that we see here, then we would have 90-degree bond angles, since carbon's p orbitals are all at 90 degrees to one another. As for the hydrogen, which would have to interact with the electron in the 2s orbital, That would have to be along some other axis, and I can't even begin to speculate about its position relative to the other carbon-hydrogen bonds. So again, we have a picture of a methane molecule which is totally inaccurate. Among its deficiencies, the hypothetical molecule fails to account for its bond angles and for the bond lengths which exist in the actual molecule as verified by experiment. In the next video lecture, we will consider a novel solution to this problem called hybridization.